Hello and welcome to section 6.5. We are closing out chapter 6 today. We're going to end it by graphing. Hopefully at this point you have a pretty good idea of how exponents work, specifically fractional exponents, radicals. We're going to look at two specifics today. That's just how you graph square roots and cube roots. We should make some connections, hopefully, when I do this. It's going to be a little bit different. It's going to be pretty formulaic, though, but I want to go ahead and relate it to how we graph quadratics in vertex form, which I'll remind you was opposite x, same y. That opposite x, same y behavior will show up again today, and actually opposite x, same y will continue to show up when we graph everything else in this class. So opposite x, same y is going to show up. Realize there's important information that we get here, graphing square roots and cube roots. You should see kind of how it works together, and like I said, it's going to be... Sorry, there's a bell. It's going to be pretty formulaic. So let's first look at what I call the parent function. Parent function is really the easiest form of the function. So let's, many of you guys don't have an idea of what the square root of x looks like. So really quickly, I'd like to just go ahead and sketch a graph of what the square root of x is going to look like. And then I also do want to talk about the domain and range of this function. Because for the first time ever, we will have a domain restriction and a range restriction. Remember, domains are talking about x values, and range is talking about y values. So, first off, f of x equals the square root of x. We really don't know anything about that, but what we are going to do is plug in values of x and see what kind of outputs we get for y. I'm going to choose some special values of x here. I'm going to use 0 first. If I plug in 0 for x, taking the square root of 0, my output is 0. Next up, I'm going to use number 1. Plugging 1 in for that function, the square root of 1 is 1. The next number that I'm going to use is not 2. The next number I'm going to use is not 3. The next number I'm going to use is 4. The number 4 I chose for a reason. Hopefully you can look at that function and see why I chose the number 4. In this case, it's a nice perfect square. So the square root of 4 is 2. I'm going to choose one more number here to get this parent graph sketched. The next number I'm going to choose, wait for it, not 5, not 6, not 7, not 8, but 9. When I chose number 9, I chose it because it is also a perfect square. The square root of 9 is 3. Mr. Wood, how do I know to choose those numbers? Can't I choose any number in the world? Sure, you can choose any number in the world. But you're going to have to use your calculator to estimate those answers. For example, square root of 2. We don't know that off the top of our head. I noticed, Mr. Wood, that you did not use any negative numbers. How about if I input negative 1 here? My output would be the square root of negative 1, which is the letter I. That's imaginary. That is a non-real root, Mr. Wood. I cannot graph imaginaries on my coordinate plane. Oh, well, what about negative 9? Can I take the square root of negative 9? No, that answer is also imaginary. So for the first time ever, we're actually going to be dealing with a domain restriction. Let's look at this graph. Plot the points that we have. 0, 0, 1, 1, 4, 2, and unfortunately on this graph, my coordinate 9, 3 is not on it. I'll go ahead and connect these dots. That's our curve. Now, here's the unique thing that happens in this graph. At no time whatsoever am I able to put in a negative number. For x, my domain is restricted. So my domain here, remember you tell the reader what x is allowed to be and what x cannot be. X is allowed to be, in this problem, greater than or equal to x to be greater than or equal to 0. In other words, it can't be negative. 0 is okay, but negative numbers are not. Should also notice that I have a domain restriction. When I'm looking at my y values are all above 0. In other words, my y values are also going to be positive in this situation. So my y must also be greater than or equal to 0. So the unique thing that happens on this problem is that we just kind of have a chunk of a graph. It starts at 0, 0. It's never going to show up anywhere over here, or over here. It's only going to exist over there in quadrant 1. Both my x's and y's are going to be out positive. We have a domain and a range restriction. That's our parent function. Now, careful. This next slide was going to look overwhelming. You don't need to copy all of it down. I'm going to explain it, and then I'll show you how it works in the example. So don't get too overwhelmed with this slide. There's going to be a lot of things that happen. All I want to look at is that form. Y equals a square root of x minus h plus k. All year long, I've been saying opposite x, same y. Look at this form and compare it to a form that you guys already know, which is this one right here, which is the vertex form of a parabola. In the vertex form of a parabola, we gave you the vertex for free, and then the A told us whether or not it opened up or down, and if it was wide or narrow. The exact same thing happens here. The A value tells us if that's going to go up or down. The opposite x is going to talk about the x value, and the same y is going to be talking about the y value. In other words, where the star will be, opposite x, same y. The star is going to move around the graph. All the graphs will look very similar to our parent function. Some might open down because the a value is negative. And again, same behavior as we had before. Same things are going to apply. How does it look? Well, I'm glad you asked. First example, f of x equals the square root of x plus 2 minus 2. F of x equals the square root of x plus 2 minus 2. Here's the way that I do these problems. We're always going to start with the parent function. And the parent function is always the easiest form of the function. So the parent is always the easiest form, the square root of x. By the way, the square root of x is what I'm picking because it's the easiest form. Very easy to do. We're going to pick these values that we used already. 4, and we'll use 9. I think 0, 1, and 4 is good enough, actually. I'll just leave it at 0, 1, and 4. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Now here's the deal. We're talking about square root, so I take the parent function of square root. That's the easiest form of the function. From the parent function, I'm going to make, and I'm going to call it a child function. So some of you guys will realize, hey, some kids are a lot like their parents. Some kids are very different than their parents. Same thing happens on these problems. Some functions are going to be very similar to their parents. Some functions are going to be very different. So what I have in red is the parent function, the easiest form of the function. That's what you've seen already. Now, our parent is going to change into a child. We're going to change that parent function. How are we going to change that parent function? Well, I'm glad you asked. The way that we're going to change that parent function is opposite x. So I'm going to write opposite x, which is minus 2, and same y, which is also minus 2. So opposite x, same y. What I'm going to go through and do is I'm going to change every x coordinate by negative 2. So 0 minus 2 is negative 2. 1 minus 2 is negative 1. 4 minus 2 is 2. Those are my new coordinates. This is my child of x. My parent was 0, 1, and 4. I've changed it. I've translated it. That's your geometry word there. I've translated it opposite x or negative 2. I've shifted those two over. Next up, looking at my y values. Again, my parent y values were 0, 1, and 2. My child y values, I will be same y, which is minus 2. This will be 0 minus 2. This will be 1 minus 2. And this will be 2 minus 2, or 0. That's my change. Look that the function is going to be similar, but it's basically just moved 2 units to the left on the x and 2 units down on the y. We will graph the child. That's the graph. F of x, square root of x plus 2 minus 2, has these coordinates in it. So that's all I need to graph. Negative 2, negative 2. Negative 2, negative 2. Negative 1, negative 1. 2, 0. Connect the dots. Remember, our graphs are just going to be a curve. They're going to have a starting point. It's a unique point. It is HK, opposite x, same y. And that's the location. We have both a domain and a range restriction. Our domain restriction is given to us within the problem. Domain, x must be greater than or equal to negative 2. X must be greater than or equal to negative 2. It's what gives me a positive root inside the radical. Notice that I can't use negative 3. Negative 3 plus 2 is negative 1. Can't take the square root of that. Negative 2 minus 2 is 0. I can take the square root of u. Anything bigger than negative 2 will work. Because of my domain restriction, I have a range restriction. That's my range. My range must be greater than or equal to negative 2. Again, it's like max and mins. I'm going up, so y has to be bigger than negative 2. If I go down, then y needs to be less than negative 2. Okay? Again, domain, range, opposite x, same y. Parent, child. It's going to be the same thing over and over and over again. It's going to be, like I said, very formulaic. Probably a little overwhelming right now. Parent, child, opposite x, same y. That's what we're going to do. Next function we're looking at. Y equals 3 times the square root of x minus 1 plus 2. Again, y equals 3 times the square root of x minus 1 plus 2. I'll give you guys a second to copy that down. And we're going to start with the parent function. Parent function is always the easiest form of the function. For square roots, it's going to be y equals the square root of x. I'm still going to use 0, 1, and 4. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. I'm always using those numbers because those are very easy for me to find the solutions to. Then I'm going to make my child function. Again, parent, child. Some look just like their kids. Some parents and kids are very similar. Some parents and kids are a lot different. The same rules apply. Opposite x, Opposite x, in this case it's going to be plus 1. Same y. In this case, we've got two changes for y. One of them is this 3. One of them is the number 2. There's two changes for y. And I'm going to ask you, hey, what are those changes? Hopefully, one of those changes you're saying is multiplied by 3, because this is 3 times the square root of x. And the other change is plus 2. You follow the rules of PIMDAS. Multiply by 3, add 2. So our change for y's is going to be multiply by 3, add 2. Multiply by 3, add 2. Again, notice that we're getting a little bit more change in this function from the parent. Go with your x values first. Here's my parent's x values. My values will change by positive 1. 0 plus 1 is 1. 1 plus 1 is 2. 4 plus 1 is 5. Every one of my x values have changed by a value of opposite x. And now my y values. My parents' y values were 0, 1, and 2. This time, this function has changed. My y changes by a multiple of 3 and addition of 2, times 3 plus 2. So I'll go 0 times 3, which is 0, plus 2. 1 times 3 is 3, plus 2 is 5. 2 times 3 is 6. 6 plus 2 is 8. So again, my parents were 0, 1, and 2. I've changed by the directions of this function. So the child is going to be changed by that multiple of 3 and the addition of 2. Each y value is multiplied by 3 and then increased by 2. I now have my new coordinates. My key point is 1, 2. I'll go ahead and graph them. 1, 2. Next coordinate is 2, 5. And my last coordinate is 5, 8. 1, 2, 3, 4, 5, 6, 7, and 8's just a little bit off. Again, these graphs have a starting point. We have both a domain and a range restriction. There's values of x that I can't have. It's given to me in the problem. My domain comes from opposite x. X must be greater than or equal to positive 1. You can see that in this graph. X is equal to 1. It's never going to be less than 1. My range is also given to me. It's same y. The range will be y is, again, we're increasing, so y is going to be greater than or equal to positive 2. Parent, opposite x, same y. Translate, making your child. Plot the points, play doctor. Again, very formulaic. Start with your parent function and translate, and you'll be fine. The math is very straightforward for these problems. All right. Link checkpoint for you guys coming up right now. There you go. I'm such a nice guy, I decided to go ahead and give you guys a negative fraction. No big deal on this. For your child, realize that it is going to change. I will tell you that this checkpoint is going to be correct if you're going down instead of up from this one. Okay, so go ahead and pause the video. I do expect you to do this problem on your green sheet with your checkpoints, and those to be turned in at the start of class. Pause the video, and then when you're ready to move forward, unpause it, please. Okay, you should have done that checkpoint. We're going to go ahead and move on to the next problem. Next problem, we are graphing the cube root of x. Mr. Wood, I just barely got down the square root of x. Why are you throwing two things at me at the same time? Because it's not that much harder. Some key differences here. Cube root of x is going to look a little bit different than the square root of x. Here's why it's going to look a little bit different than the square root of x. The square root of x is an even function. The cube root of x is an odd function. There's unique behaviors, and we saw this with polynomial functions. End behavior differs for polynomial functions. Different things happen with odd numbered functions than happen with even numbered functions. At honors pre-calc and calculus level, you'll really get into odd and even functions. At this level, just realize that there's a difference between odd and even functions. The biggest difference, I think I might have made my XY chart too big. The biggest difference between the square root that we just did and the cube root is this. Well, 0, what's the cube root of 0? 0. How about 1? What's the cube root of 1? That's also 1. Mr. Wood, you said there was a big difference. I'm not seeing a big difference here. Yeah, there's not yet. What's the next number I'm going to choose? On my square root, my next number was 4. For my cube root, that number's not going to be 4. For my cube root, that number's going to be 8. Why did I choose 8 there? The reason I chose 8 is because that is a perfect cube. The cube root of 8 is 2. And on the last problem, that's all I did. I had 3, and we kind of went from there. Here's the big difference with cube roots. What's the cube root of negative 1? Don't say no solution. The cube root of negative 1 is negative 1. Why? Because negative 1 times negative 1 times negative 1 is negative 1. The cube root of negative 8 is negative 2. Negative 2 times negative 2 times negative 2 is negative 8. So now, hopefully you can see visually, we are not going to have our domain restriction anymore. There's not going to be a domain restriction. I can pick any number, positive or negative and 0 for x, and I can get some sort of output for it. I'm not restricted anymore. Let's see what this parent function is going to look like. 0, 0, realize this graph is scaled by 2. Just a heads up if you're trying to sketch this graph. So 1, 1 for me on this graph is going to be there. Negative 1 is going to be there. And then negative 8, what do I got? 8, 2, 4, 6, and 8. And then positive 2 is going to be there. And then negative 2, negative 4, negative 6, and negative 8, negative 2 is going to be here for me. So this graph is really going to look like that. That looks a lot different. Yeah, the reason it looks a lot different is because we can actually cube root negatives. It doesn't look much different at all in quadrant 1. It just gets thinner faster because we're taking a cube root instead of a square root. That above looks just like the square root. We now have below because we can take the cube root of negative numbers. So we have two sides of this graph. When we have two sides, there really is not going to be a domain restriction. So x, once again, equals all real numbers. Range, y, in this case, is not going to be restricted. I can have zeros, I can have ones, I can have positives, I can have negatives in my y's. I can have zeros, I can have positives, I can have negatives in my x's. No restriction here. So our cube root has no restrictions. Really, our square root's the finicky one. It's the one that has both a domain and a range restriction. We're going to play the same game, by the way. Parent, child, translate. A tells us it goes up or down. Opposite x again. Same y again. We're going to do the exact same thing that we've done all the way around. In fact, you probably already have that written down for your square root. It's going to look exactly the same as your cube root. We just have to remember to use positive and negative values because in this case we don't have the restriction. So really you just need to plot a couple more points. What's it going to look like? Well, I'm glad you asked. Mr. Wood, I didn't really ask. f of x equals the cube root of x plus 2 minus 2. Start with your parent function. Parent function is the easiest form of the function. I'll give you guys a second to finish copying that down. All right. Easiest form of the function is cube root of x. Pick perfect cubes. 0, 1, 8, -8, -1. Your outputs, 0, 1, 2, that one's -2, that one's -1. Should make sense to you that I pick perfect cubes. I pick easy things so I don't have to use my calculator to do something difficult. Remember, no calcs on this test. I think I put too many on there, but that's okay. Oh, we have the rest of that. All right, there's my parent function. Once again, we're going to make a child. That doesn't sound right. We're going to make a child graph. Opposite x is the way we're going to do that. Opposite x, we will change every single one of our x values by opposite x, so -2. Every single one of these x values will change or be translated by a -2. So this whole graph will move 2 units to the left on our x-axis. So 0 minus 2, -2. 1 minus 2, -1. 8 minus 2, 6. -8 minus 2, -10. -1 minus 2, -3. Notice, every single one of my x values has been translated 2 units to the left. How are we going to move the y's? I don't know. Same y maybe? It's almost as if I've been talking about it all year long. Every single one of your y values from your parent will change or go 2 units down on your y-axis. Most difficult math you're going to do, 0 minus 2, -2, 1 minus 2, -1, 2 minus 2, 0, -2 minus 2, -4, -1 minus 3, -3. Parent in blue, child in Christmas colors here. We're going to go ahead and plot the points. I only want to see the child graph. I don't want to see the parent function. We did that on the previous one. Go ahead and plot your points and connect the dots. -2, once again, I am scaled by 2s on my axis. I don't know how you want to scale yours, and that is up to you. -2, -2 for me is right there. -1, -1 is right there. 6, 0 is there for me. -10, -4 is off my chart about here. And -3, -3 is there. Go ahead and connect the dots. And we have our graph sketched. Last part, play doctor, domain and range. And domain and range is easy for this cubic function, cube root function. X can be anything we want, and Y will be anything we want it to be. All real numbers and all real numbers. Kind of not that hard. Next problem. Oh, this is a good one. Y equals -2 cube root of x minus 3 minus 2. Y equals -2 cube root of x minus 3 minus 2. That's the next function we're doing. Give you guys a second to copy that down. Maybe set up this problem. You might need to pause the video because I already have all this stuff written down. Make your XY chart. Probably want to get started making your parent function also. I just realized that I haven't included today's secret password. Today's secret password is Go Dodgers. Go Dodgers is the secret password for this video. All right. Start with your parent function here. Parent function is always the easiest form of the function. Parent function in this case will be the cube root of x. Again, parent function comes from whatever's easiest. So cube root of x, again, we're going to start with perfect cubes here. 0, 1, 8, then negative 8 and negative 1. I picked those because they are perfect cubes. And it's very easy for me to do in my head. Next up, make the chop. Hopefully you'll agree with me right now. Hey, this graph is probably, out of all the graphs we've done so far, this one's going to be the most changed from the parent function. Maybe your checkpoint of negative 1/2 might have been the most changed. So, how are we changing here? Still the same rules. Opposite x. In this case, negative 3. Opposite x is going to be positive 3. Take every value of x, and this time it will be translated 3 units to the right. 0 plus 3, 1 plus 3, 8 plus 3, negative 8 plus 3, negative 1 plus 3. Now I'm going to change my y's. So every y will change. I've got multiple changes on my y's. I've got to change by a multiple of 2, because again, that says negative 2 times the cube root. And then I have a change of negative 2. So this time my y's are going to change by a lot. I'm going to multiply by negative 2. And then I'm going to subtract 2. That's a big change. Remember I said, hey, some of these graphs are just like their parents. Some of these graphs are going to be very different from their parents. This one's going to be pretty different. Every y value will change by multiplying by negative 2 and then dropping down 2 units. So 0 times negative 2 is 0. 0 minus 2 is negative 2. Next up, 1 times negative 2 is negative 2. Negative 2 minus 2 is negative 4. Next up, 2 times negative 2 is negative 4. Negative 4 minus 2 is negative 6. Next up, negative 2 times negative 2 is positive 4. Positive 4 minus 2 is positive 2. Lastly, I have negative 1 times negative 2, which is positive 2. Positive 2 minus 2 is 0. So those are my new coordinates. Again, opposite x, same y. Y had a little bit more change there. Plot those coordinates and graph. 3, negative 2. Again, I'm scaled by 2's here. Three, negative 2. 3, negative 2. 4, negative 4. 11, which is off my graph. Down here, negative 6. I'm going to kind of try to put it over there. It's off my graph, though. I have negative 5, positive 2. And lastly, I have negative, wait a minute. I have a mistake somewhere. Where is my mistake? Negative 5, positive 2. 2, 0, that's not correct. Oh, maybe, yeah, it is. I'm sorry. I do not have a mistake. 2, 0, I just don't know how to plot points. There we go. 2, 0. We need to connect the dots. Remember, that guy was off my board a bit. And there's a sketch of my graph. All the coordinates fall on one line. Let's see, this looks different than our other ones. Again, the negative is the reason we kind of switched that behavior. And our domain and range. Domain and range for cube roots are always all real numbers. Again, the finicky one is the square root. Square root has a domain and a range restriction. All right, that's kind of it. Opposite x, same y. And then you guys got another checkpoint coming here. You guys go nuts. Y equals 2 cube root of x plus 1. Again, this should be done on your checkpoint. This should be done on your green sheet of paper. Go ahead and pause the video and do the problem. I'll expect these problems to be done at the start of class tomorrow. At this point, you should have 2 checkpoints, and you should also have the password. I think that's about it. So go ahead and pause the video. Actually, I think that's it with this whole video. Let me double check that real quick. Yeah, I got one more problem for you. So go ahead and pause the video. Complete this checkpoint. This is checkpoint number 2 for you. Hopefully you unpause the video. You finish that checkpoint. And now there is your 3rd checkpoint. Okay? That says exit. I really want that to be your 3rd checkpoint. Okay? So those are the 3 problems you need to have done to start a class. You should be pretty clear about how we're graphing this stuff. We will touch up on it tomorrow in class, and we're going to talk a little bit more about the domain and range stuff. Okay? Good luck. See you tomorrow.